Okay, so for this lecture, we're going to talk about the idea of a magnetic force acting on a current in a wire. And again, if you ever have any questions during the lecture, just jot them down on the side of your notes, or you can write them in the discussion question part. So if you have a current, then the current always has a magnetic field around it. We talked about that before. And so if you have a current that has an existing magnetic field and you place it in an external magnetic field, then those two fields will interact and the wire that's carrying the current will actually experience a force. So if the wire carrying a current is placed in an external magnetic field, then it will experience magnetic force. And that's because you'll have two magnetic fields interacting with each other, and anytime you have two magnetic fields interacting with each other, they're either going to attract each other or they're going to repel each other. So let's look at the equation for the magnetic force on a wire. We've already looked at the equation for the magnetic force on a charged particle, and the equation for the wire comes out of that. So I am going to go through and do a derivation of the magnetic force on a wire, and I will box the final equation. Okay, so we started off, and we already know this equation, that FB is equal to QVB sine of theta, where FB is our magnetic force, Q is the charge of the particle, V is the velocity, how fast it's moving, B is our magnetic field, and sine of theta is the angle between our velocity and our magnetic field. Now, if we go back to the base definition of velocity, velocity is just distance over time. And I'm going to be a little bit particular. I'm going to call velocity just length over time. And what I'm going to do is I'm going to insert this. Again, you don't have to write down this derivation, but it's just kind of giving you an idea of where it comes from. So if I substituted that in, I would get FB is equal to Q times length over time, B sine of theta. Now, as we're looking at the magnetic force on a wire doesn't just carry a charge that's moving, it carries many charges that are moving. And when you have several charges that are moving, we call that current. And if you look right here, this idea of charge over time is current. Okay, that's something we looked at in the circuits unit. So charge over time is current. And so the equation actually looks like ILV sine theta. But for some reason, the way every textbook always writes it is the magnetic force on a wire is equal to the external magnetic field times the current times the length of wire that is in that magnetic field times sine of theta. So this is kind of the final equation, but it's thought it'd be interesting to look at the derivation. Again, if we just looked at what these quantities are, let's just write them here. So B is the external magnetic field. I is the current. L is the length of wire in the field. And theta is going to be the angle between the magnetic field and the current, or the length of the wire. Again, with magnetic force, we're going to use right-hand rule number 2 to indicate the direction of force with relationship to the magnetic field and the velocity. In this case, the velocity is always going to be the same direction as current. So when you have your magnetic force, it's still going to be that the thumb is your magnetic force, but now velocity and current are the same thing, and magnetic field is still the middle finger. So we're going to try one example during this lecture of magnetic force on a wire, and then we'll do some more examples in class. So for this example, it says a straight wire, 50 centimeters long, conducts a current of 4 amps vertically up. If the wire experiences a force of 0.001 newtons eastward, what is the magnitude and direction of the magnetic field. So in this problem, we're specifically asked what's the numerical value of the magnetic field and what is the direction. So let's just first start off by identifying our quantities. I have 50 centimeters, and we can't be in centimeters. We have to be in the proper units of meters. So the length is going to be 0.5 meters. And it conducts a current of 4 amps. Amps is my current value, so I is equal to 4. We're told it goes vertically up if the wire experiences a force of 0.001 newtons, so that is my FB. And eastward, what's the direction, magnitude direction of the magnetic field? So let's just start off, before we look at the magnitude, let's just draw it. It's a good habit to always draw what's going on. So we're told that the current of 4 amps is vertically up. So I have this current that goes upwards. And the wire experiences a force of 0.001 newtons eastward. So my magnetic force is this direction. And so if we just start off by looking at the right-hand rule, your current is going to be going upwards. And your magnetic force is going to the right. So that's my thumb. So I always start off with just using my current or my velocity, doing that initial direction. So initially, my current's going up, but I need my magnetic force to point to the right. So I'm going to rotate my hand so that my thumb, my magnetic force, is pointing to the right, and I end up with my middle finger coming out of the page. So that indicates to me that my magnetic field is going to be going out of the page, and I can indicate that with a dot, or I could say out. Now to figure out the actual magnitude or the numerical value, that's where I'm going to look at my equation. FB is equal to BIL sine of theta. So my FB is 0.001. It's going to equal B. My current is 4. My length is 0.5. And I have a 90-degree angle between my magnetic field and my current, and between my magnetic force and my current and everything, so it's going to be sine of 90. And sine of 90 is just 1. So go ahead and take a moment and calculate out what this is. If you need to pause the video to try and calculate it out. Don't just cheat and wait for my answer. So the magnetic field value that I got was 5 times 10 to the negative 4 Teslas. And again, that direction is out. So I would indicate that with a dot, or I'd write the word out. Okay? So when we get back to class, we'll look at some more examples of magnetic force on a wire.